Hello, dear students and all the listeners. Good morning, good afternoon, and good evening, depending on where you are. Today, I am going to talk about basics of nuclear science, radiation, radioactivity, and nuclear reactions. I am chairman of Sri Lanka Atomic Energy Board. So before we start talking about the radiation or the discovery of radioactivity, I think we have to go back and check the chronology or the timeline. What paved the way for the discovery of radioactivity. So if you summarize the things happened at the end of the 19th century and the beginning of 20th century, remember the Röntgen discovered X-rays. So I always believe that discovery of radioactivity also indirectly involved with the discovery of the X-rays. So then only the Becquerel discovers the radioactivity. I'll talk about it little later. Then the Thomson discovered the electron. So that was much later, even before the discovery of X-rays as well as the discovery of radioactivity. Then, of course, this is the tremendous era for the development of radioactivity. Marie Curie and her husband discovered together with his husband, they discovered polonium, radium. Then Becquerel discovered that beta rays are really electrons. Then even Rutherford discovered that the alpha particles are helium nuclei, and so on and so forth. Now we are at the era of, I mean, enormous amount of uses of radioactivity in all sorts of fields, in medical field, technology, industrial, everywhere, agriculture. Now even I think Marie Curie never thought that radioactivity and radiation would be so beneficial to mankind. So I will start with the discovery of X-rays. So because I believe that discovery of X-rays really paved the way for the discovery of radioactivity as well. So we all know that when Ranjan was working with this cathode rays, remember those days at that era, working with cathode rays were like a fashion for all scientists. So, especially the cathode ray tubes were manufactured and done by crooks. Sometimes we don't give the credit that crooks should get, but we talk about the scientists, but not the people who behind the scene. So, when Ranjan was working with this cathode ray tube, as we all know, suddenly he found out some unknown rays are emitting, and then he noticed that these unknown rays are emanating or coming at the point where the electron beam stops. So the legend say, actually the story says, when he discovered this, for about 6 or 7 days he has not gone home, he has not visited his home. So finally, I think since he didn't go, since he didn't go to his place, wife has come to see him. So when Ranjan found out these X-rays, this is the left-hand side. You will see the first X-ray photograph. So he took the palm, or I think he has asked his wife to shuffle her palm, or maybe wife has volunteered. I don't know which is which, but whatever it is, this was the first X-ray picture that world has seen. So that happened in 1985, November 8th. So this is actually a current X-ray tube. The principle behind even a modern X-ray tube is the same principle that cathode ray tube had, maybe a little bit of modifications. So electrons are coming from the filament. It's called thermionic electrons. So when you heat the filament, electrons jumps out from the filament, then you accelerate the electrons and then you allow the electrons to stop suddenly in a target. So by the time that happens, a small amount of energy of the electron is converted to X-rays, because we have now we all know in science, when charge particle accelerates or charge particles are suddenly stopped, they emit electromagnetic radiation. So this wavelength or the frequency of emitted electromagnetic radiation depends on the energy that you lose. So that's why we have to accelerate the electrons to high voltage or high potential difference in the order of kilo electron volts, because in order to create an X-ray photon, you need a loss of kinetic energy in the order of kilo electron volts. So so this is again the first X-ray photograph of Ranjan's wife's palm. So even Ranjan Weiss was amused. Even at that time, all people around the world, especially in Europe, actually they were surprised, because this was the first time that they had seen the skeleton of a human being. So then even Ranjan's wife has once said, she was interviewed by a newspaper. She has said that she has seen the death, because only after you die you can see the, of course you can't see, but others can. Once you are buried, after several months or several maybe after 1 year, you can see the skeleton. So she has told the newspapers that she has seen the death. So then this is the Ranjan's actually wife's this is not a tube or anything like that. This is the wedding ring. X-rays didn't go through the wedding ring, but X-ray went through the flesh and blood, because of the contrast, because the bones contain calcium, so X-rays, calcium absorbs X-rays, and you get the contrast. So then what Becquerel did was, actually Becquerel had a little bit of a wrong idea at that time, even though he discovered radioactivity. So Becquerel actually was the inventor of phosphorescence. Now there are fluorescent materials. Phosphorescence means even you turn off the incident light, still you can get the light inside this phosphorescence materials. I think we all have seen that, even in exhibitions and even lot of places you see they emit visible light even after the incident light is turned off, because the atoms and molecules are excited. So when they de-excite, they emit radiation, and they emit part of the radiation falls into the visible light region. So Becquerel had a wrong idea. Actually, he thought even when you expose some minerals to sunlight, he thought they might emit these unknown X-rays. That was his actually postulate, or he thought, that is like assumption. He thought that when you expose these minerals to sunlight, they might emit these unknown rays, because even Ranjan had named these rays, maybe later people have named it as X-rays, but you can call them as Ranjan rays also, because Ranjan was the person who discovered. So X means unknown. No, now even in mathematics, when you are solving equations, normally we use variable X to illustrate or to define the unknown. So X means unknown. Now we all know how it happens, or how they are generated, but at that time it was unknown. So Ranjan thought that when you expose these minerals to sunlight, they might emit X-rays. So in order to test this idea, he had a photographic plate here. You can see it was covered by a black cloth because you don't want the sunlight to come and expose your expose your film directly. So you have to cover this by black cloth so the sunlight get absorbed. Then on top of that, he put fortunately he used uranium containing crystals or uranium containing mineral. That was the starting point. Accidentally. This all discovered accidentally. You know, even X-rays were discovered accidentally. Your radioactivity is also accidental discovery. Nobody wanted to discover, but they are, even though they are very, very great discoveries, scientists have found them accidentally. So he used this uranium containing mineral and then he wanted to expose this to sunlight. So if sunlight incident on the uranium mineral, if it emit X-rays, then X-rays should go through the black cloth because X-rays are penetrating. Then you should be able to see patches or shadows on the photographic plate. So he did this experiment. The story says actually, to his luck, when he wanted to test this, there was a cloud cover. You see, there was cloud cover. So therefore, maybe he could not do this experiment, or he could not test this his hypothesis. His hypothesis means when sunlight incident on the uranium minerals, it should emit X-rays. Now we know that is not true because sunlight, normal light can't produce X-rays because X-rays, photons, X-rays energies are higher than the normal visible light. Anyway, sometimes even your postulates or the experimental decisions or the observations don't tally with your theory. Sometimes you can discover very great things. So as science students, young students, I am telling you that even negative results sometimes play an important role. Sometimes even in life you can't get all positive things. Even negative things also you can learn a lot. So Becquerel got the Nobel Prize even from his wrong assumption. So since there was cloud cover, he could not perform this experiment. So I think what he did was he put everything in a drawer and closed the drawer and went home. And after several days, cloud cover went off. Then suddenly he noticed already this film, the photographic films were exposed to something. So that was the discovery. So as a scientist, even young students, you should always be vigilant because there are unexpected things happen in science. So sometimes if you miss those, you will lose the Nobel Prize also because you have to be always vigilant and you have to be very careful of testing your observations and experimental know-how that you get. So, so when he put everything in the drawer, and after several days, he came back and took the whole thing out, thinking that he wanted to expose these uranium minerals to sunlight. But to his surprise, he noticed actually already the photographic films have got patches or got exposed to something. So this is actually the radioactive. That was the discovery of. So Becquerel thought that this was in a drawer, and sunlight could not reach into the drawer. So you don't expect magic in sciences. So definitely he thought this reason for this exposure of film, photographic film, he thought maybe the uranium minerals also emit something because that is the only conclusion that one could derive because it was in the inside the drawer and it was in the dark, so sunlight could not enter into the drawer. So if something has happened to the film, then the system itself should emit something. So that was his conclusion, and that was the right conclusion, because there is nothing else you can think of, no? Because if it is in an enclosed room, and if you don't expect anybody to interfere, then if something happens, it should come from inside, not from outside. So this is again the timeline of the discovery. Ranjan 1895 X-rays, 1896 Becquerel discovers uranium salt. Then Marie Curie and others jumped at this, and then they did a lot of work on radioactivity, as we all know. So Marie became the first woman to receive doctorate degree in France. Becquerel shared the Nobel Prize in Physics with Marie Curie, discovering of this spontaneous radioactivity. You know, Marie Curie received two Nobel Prizes, one for physics and one for chemistry. So this is a little bit of history for you all. So this is this Becquerel's film, really. That happened in 1896 March, 1st of March. So you can see for some reason Becquerel noticed some patches or shadows on the photographic film. So definitely he thought, as correctly, the uranium salt should emit something, unknown something. Even at that time, it was unknown. So this is the discovery of radioactivity. So we honor Becquerel as the discoverer of radioactivity, even though Marie Curie and her husband did a lot of work related to radioactivity. So again, this is again history, 1896 Becquerel, then 1898 Marie Curie and husband Pierre Curie coined. Actually, they were the one who gave this word radioactivity. I think the word comes from radiation, because radiation activity. Radioactivity means radiation comes out from these minerals, and it is activity. So radioactivity. So they were the people who found the elements radium and polonium. Radium and polonium. The word radium comes from actually I think Greek word rays. Radium means rays, emanating rays. Rays are coming out. Polonium she has named to honor her motherland, for Poland, because she was a Polish. So to honor her motherland, he named the other element as polonium. Radium means the rays, emanating rays. So, but unfortunately, as you all know, they didn't know at that time the hazards of radioactivity. And now we all know, we never get exposed to radiation deliberately. Of course, when you become sick, or if you are a cancer patient, sometimes you have to expose to radiation. But what can you do? Because you have to take the risk. So at that time, actually, Marie Curie and husband, they never thought that radioactivity, exposing to this radiation, is a hazard. So he developed, I think, from leukemia. Even before that, her husband died in a traffic accident, horse and buggy accident. So story says actually he was also very sick at that time. So unfortunately, they died, but they had done a immense service to the field of radioactivity and radiation. So just to finish that section, so I thought that I should show you the most prominent people or the important people that led to the discovery of radioactivity, as well as the experiments done later. Ranjan, actually, that's why I started with X-rays, because I believe if Ranjan had not discovered X-rays, radioactivity wouldn't have discovered at that time, because the discovery of X-rays indirectly paved the way for the discovery of radioactivity as well, because Becquerel wanted to test the emission of X-rays, these unknown rays. Maybe at that time it was like a passion for all scientists to find out to get these unknown rays. Because Ranjan found these unknown rays when he was working with the cathode ray tube. So other scientists wanted to reproduce this. Can we get these unknown rays even from some other activity? Does X-rays comes only when the electrons are suddenly stopped? Can't we get X-rays from other means? Maybe that was their thought. So that paved the way for Becquerel to discover radioactivity, and then rest is history now. Okay, so before we go to the radioactivity, I think we have to think about the atom and the nucleus. As we all know, actual radioactivity is a process coming out from the nucleus. It's not an atomic thing. That's the difference. You know, when you have atoms, you have if you didn't have a nucleus, then there's no nuclear physics as well, and radioactivity is also part and parcel will be forgotten, because if you have these new radiations which comes out, alpha, beta, gamma, they come from the nucleus itself, not from the atomic transitions or anything. So if you go back to the model of the atom, so this is the Thomson model of the atom. As you all know, now we know this is not correct. So Thomson already had discovered the electrons, no? And then because 1897. So this model came in 1904. So Thomson has already discovered the electrons, and according to his experimental results, we all know that the electrons are basically negatively charged. That's why it got attracted to the positive anode. So then Thomson thought there are electrons in matter. I mean, because that's why electrons are popping out from the matter. Then if you look at the gross matter day to day around us, things are neutral. So if things are neutral, Thomson thought there should be a positive something. Because if you had only electrons in an atom, then it should be charged. You should be able to charge. Of course, you can charge them, but grossly the matter is neutral. So therefore, he thought there should be a positive charge somewhere, because positive and negative should balance it with each other. Net charge should be zero. But he didn't know where this positive charge was assembled. So he thought the positive charge is sort of a smeared. That's why it's called the plum pudding model. Electrons are like plums. This is the pudding. You know, in puddings there are plums. So, so according to Thomson model, the positive charge is distributed, and he didn't know where this positive charge came. So Rutherford was a student of Thomson, as we all know. So Rutherford wanted to test this theory, this model, Thomson's model, his supervisor, so his teacher's model. He wanted to test whether that model is right or wrong. So this is basically history, all of us know. So luckily at this time radioactivity has been found. Otherwise, how can you find out the details of a small thing? Now you know you can't throw stones and find out the model of the atom. They should be compatible. So Rutherford used these alpha particles, and he had a very thin foil, and then he allowed the alpha particles incident on the thin foil, and then he measured the scattered alpha particles. So this foil has to be very thin, otherwise alpha particle will stop inside, and it is made out of gold. And when you have gold, you know the gold nuclei Z number is large, the atomic number is large. So so that is also one advantage. And the other advantage is from gold you can make very thin foils. So from these experiments, we don't have to go into details. He found that the Thomson model was incorrect. because of the reason that when he did according to Thomson model, the sky incident delta particle should be deflected with small angles because all positive charge is smeared or positive charge is distributed. It's not concentrated. It's not concentrated like the model that we know now. So Rutherford model, right? In the Rutherford model, actually, he noticed these some alpha particles came back. That was the turning point, actually. So some alpha particles came back. That is called backscattering. So from that, Rutherford thought there the positive charge should be concentrated. It's like hitting something. In his own words, Rutherford has written when he found alpha particles got backscattered or came back, he thought he sort of he wrote this thing or the what he noticed like this. It is like you bombard cannons or shells onto a tissue paper, and the cannon or bullets come back at you. We never expect that because it's a tissue paper. If you shoot cannons or any bullets, they should go through it. What the hell they come back? Why the hell they come back? So these some bullets came back like so. Some alpha particles came back. So from his experimental results, he concluded that the positive charge is concentrated inside the atom. So that was the model. Even today, of course, now we have the quantum models, but basically Rutherford model is valid. We have the nucleus at the center. Electrons are revolving around the nucleus. So at that time, scientists were happy about the model also because that is similar or compatible with even the solar model. Because even the solar model, we have the sun at the center and the planets are revolving around the sun. So this model is also very similar. Always, as scientists, when you have similar things, when you have analogy, we call it analogy. When you have similar things happening or repetitions of nature, scientists like them, like that idea or like that thing happening. The forces are different, gravitational model and this thing, but it is the same model. So therefore, this is one of the animations. Actually, luckily they have the radioactivity, so he used alpha particles, and he shot those alpha particles to a gold foil, and then he noticed that some alpha particles backscattered. Most of them went through with small angles, deflections or deviations, but some came back. So then you can easily argue that if something comes back at you, then you have hit some hard. Actually, alpha particles never got reached or they never came to the near the nucleus because the energies are not enough. But if something comes back at you, that means you are looking at some hard thing, no? Now, if you throw a ball to a wall, the ball comes back because the ball hits on the wall. Otherwise, it should go through. So this is the starting point of the model of the atom. So I just wanted to recollect you that because if you don't have the correct model of the atom, then of course it's difficult to study the radiation as well. So this is the simple model all of us know, even children, even younger children knows this model. We have the nucleus at the center and the electrons are revolving around the nucleus. Okay, then comes to the radioactivity. So scientists have discovered there are basically three types. Basically three types, but of course, if you go into details, there are more than that. So they emitted alpha particles. Actually, at that time, scientists didn't know what they were. They didn't know what alpha particles were. That's why they used these first letters of the Greek alphabet to name this unknown radiation. Because alpha, beta, gamma, they are the first letters of the Greek alphabet. So just without doing anything, they said, ah, this is alpha, this is beta, and this is gamma. Now, even WHO has named this COVID-19 also, these different types of COVID-19 by Greek alphabet or Greek letters, alpha, beta, gamma. So I will show you now how scientists have found that the alpha particles are helium nuclei. So alpha particles are basically helium nuclei. Helium nuclei means you have two protons and two neutrons. So this is example of alpha decay. Uranium decaying into thorium, and then this is the alpha particle. So this is one way that the nuclei disintegrate or decay. Why they decay? Because they want to become stable. Actually, everything in this world, if you lose energy, means you want to become stable. Even when you get angry, you blackguard others, sometimes you hit others to lose your energy. I mean, these are not good things. But if you have more energy, nature always want to release that energy and come to a stable situation. Nature does not want to have, aggregate lot of energy. Somehow you have to dissipate the energy. So alpha particles are coming because of this. This what we call the transformation. This radioactivity played a very important role in understanding the nucleus as well. If nothing came out from the nucleus, how can we study anything? In life also, in day-to-day life, if you want to study some unknown thing, of course, there are only two ways of studying unknown thing. One way is the system. If the system gives you something, then by studying those things, we can conclude what type of thing that these particles or radiations are coming. And the other way of studying unknown thing is you shoot something. You throw things at him, at that system, and then you want to find out how they scatter, whether they can come back or whether they scatter, whether they goes through, or whether they deflect with the large angles or small angles. Then you can get some idea about the system. Even in life, this is true. No, now, how do we understand a human being? If you want to understand the human being should emit something. Emit doesn't mean that real emission. We try to understand the person by the look, or how he smiles, how he talks, how we treat the others. We say, he's a nice person. We say he's a bad person. So we study the person from the things that the person gives out. That is one way. Other way is you throw things at. That is also one way of studying a human being. Sometimes you think this person is very good, but if you throw things, if you blackguard him, he might get angry. Otherwise, he looks like a very calm person. So even in nuclear and any physics or whatever the system, these are the two ways of studying unknown thing. Either system has to give something, or you have to shoot something at the system and try to understand. So radioactivity, if radioactivity was not discovered and if radioactivity was not there, we cannot study about the nucleus because the nuclei emit this radiation. And the other most important thing is actually this radioactivity is a spontaneous process. Spontaneous process. That's why I call spontaneous means there's no cause. That also played a very surprising thing for scientists at that time. Some scientists were puzzled. How come this radiation suddenly comes out? Because nobody has done anything. Because some scientists thought to get something out, you have to have some cause. In chemical reactions, when you heat something, you can get something. So radioactivity is a spontaneous thing. It happens without any disturbance from outside. That's why I call spontaneous. So sometimes some scientists thought that mass energy conservation is not valid because things happen just like this. You can't find a reason for that. Actually, Rutherford and Soddy, they were the first person to say that this radioactivity is a spontaneous. It is a statistical process. It works with probability. You don't have to do anything. It just comes out. Even today, when you have radioactive material, it just comes out. Nobody is pushing it. Nobody is heating it. Nobody is increasing the pressure. It happens. So that is also one thing that you have to understand when you think of radioactivity. Then the other most important thing, actually, these chemical and biological reactions are very different from nuclear reactions. Now, chemical and biological reactions, always you can't change the element. In chemical and biological reactions, chemicals won't change. That's why, in a chemical and biological reaction, you balance. If you have 4 carbon atoms in the left hand side, you should have 4 carbon atoms in the right hand side. So, chemical and biological reactions can form compounds, not compounds, because the identity of the element does not change. Identity of the element does not change. But when radioactivity happens, actually the element changes. To change a element, you have to change the nucleus. Without changing the nucleus, you can't change the atom. Of course, you can, in chemistry, you can make ions. You can get electrons out. But nothing happens to the nucleus. You get the same element with ion, positive ion, no negative ion, no doubly ionized. But you can't lose, or you can't change the identity of an element. So that also puzzled scientists, because earlier scientists thought there was some chemist they call alchemist. They gave an idea. They said in the world or in the universe you can't change atoms. Atoms, identity of the atoms is there. Atom identity of the atom is intact. But radioactivity and nuclear reactions uh, change the whole scenario. Because you see here, from uranium you can get thorium. In chemical and biological reaction is a dream. You cannot get thorium out of uranium. How can you? You can make uranium compounds. So that is also, those are very important things that you want to know about when you study radiation. It's a nuclear scenario. It's a nuclear game. It's not the atomic thing. Even from the energies we can conclude that. And by way of emitting this radiation, the atom changes. Uranium to thorium, then to something else, then to something else. Finally, it comes to a stable element. But whatever it is, chemistry and biology, you cannot do such a thing. It is impossible. So then scientists have found this first type of radiation, alpha particles or helium nuclei. Then they found actually so-called beta particles. Then they found these beta particles are merely electrons. Of course, some nuclei emit positrons, positive electron. Positron means the antiparticle of the positron is the antiparticle of the electron. So some nuclei emit electrons, some nuclei emit positrons. We will see later why this happens. And it emit gamma rays also. Actually, gamma rays are emitted when in this radioactivity bargain, we give the name parent and the daughter. You have the first, if a nucleus decays to something else, that is called, first one is called the parent. Other one is called the daughter. So when parent decays to the daughter can go to excited states. Similar to in the atoms, there are energy levels, no? Electrons occupy in different energy levels. All electrons won't occupy in the same level. If that happens, there's no chemistry. I mean, all periodic table people categorize elements into the position of the periodic table depending on the electron configuration. If you think of sodium, sodium has 11 electrons. If all 11 electrons are in the same level, I mean, sodium will not behave as it is. You know, 2 electrons go into the first level, then the 8, and then the last electron is vacant. That's why sodium make ions. So similar to atoms, even nuclei have energy levels. Similar. Physics is different, but it's a uh, similar configuration. So therefore, when a parent decays to a daughter, it can go to excited state. So when it goes to excited state, it can decay back to other lower states by emitting gamma rays. In atoms, similar thing happens. When electrons are excited to higher states, when they come to lower states, they emit either light, visible light, infrared heat, ultraviolet, and so on. Of course, atomic transition cannot give you a gamma ray. Gamma ray has energy of MeV order, mega electron volt. So if a gamma ray comes, it should come from the nucleus. So we have alpha decay. Beta decay we divide normally into two parts: beta minus decay, the electrons, beta plus decay, positrons. Then we have the gamma decay. Then there's another process that don't talk about it. That is called electron capture. Electron capture means protons in a nucleus uh, occasionally can capture electron from the orbitals. You know, according to the quantum model of the atom, there is a probability or there is a chance that the electron exists near the nucleus. Because according to the quantum model, we treat the electron as a wave, not as a particle. So the electrons, when they come close to the nucleus, the proton can capture the electron. That is called electron capture. Electron capture. Because positive protons like the electrons. Why not? Positives like negatives. So proton occasionally can capture orbital electron. So when it captures orbital electron, then also the nucleus changes because you capture electron from the orbits. It is similar to a positron decay. We will see later. So these are the so-called 1, 2, 3, 4, 5 processes. Sometimes we say only alpha, beta, and gamma. But really speaking, beta is divided into two sections or two parts. And there's another process called electron capture, which is in a way that we get the same daughter. Now, normal electron capture can happen in a little heavy nuclei because in heavy nuclei, the electron clouds are closer to the nucleus. So suddenly a proton can capture electron. So this is an animation of alpha decay. Unstable plutonium emits alpha particle and then parent change to the daughter. This is a animation of a alpha decay. This is the animation of a beta decay. Famous carbon 14 decays to nitrogen 14 by emitting a electron, and then when beta decay happens, there's another particle emits either neutrino or electron neutrino or electron antineutrino. Alpha decay is basically a two-body process. Parent changes to a daughter and then emits alpha particle. But in beta decay, you have the daughter and the electron or the positron and accompanying neutrino antineutrino. So beta decay is a three-body process. That is also very interesting. To understand that, you have to go to this what you call the lepton number conservation. Even that scientists had difficulty in understanding. You know, at the beginning when beta decay was discovered, they didn't observe these neutrinos because neutrinos are uncharged. Neutrinos you can't detect. Charged particles always you can detect. Uncharged particles, you can't detect them directly. You have to detect them indirectly. So the neutrinos, even the neutrinos came out in beta decay, they could not detect them. So it got unnoticed. Then there were big problems in mass energy conservation, because if you lose one guy from a decay, then how can you balance? It's like that if you have 1,000 rupees, if you give that 1,000 rupees to three people, and if you miss one person, you can't conserve your money. Say you give 50 rupees to someone, 40 rupees to the other one, 10 rupees to the other one. If you miss the third one, 10 rupees, then you can't find out, you can't have check and balances. So if you miss one guy, then it's very difficult to conserve mass energy. That I am not going to talk about it. But this is the animation of a beta decay. This is the animation of a gamma decay. Now actually always you have to understand alpha gamma rays comes subsequently or after a alpha or a beta decay. Uh, because alpha decay means emits a helium nucleus. So gamma rays always comes when the daughter goes to excited state. If the parent decays to the ground state of daughter, you don't get gamma rays. Now some radioactive decays are like that. You don't get gamma rays. If you get gamma rays, it's easy to detect. Because gamma rays penetrate, there are a lot of ways of detecting gammas. Alpha particles are difficult because alpha particles loses energy within a very short distance because it's highly charged. But gamma rays, they are photons, so they penetrate. So nowadays, you can measure energies of gamma rays very, very precisely. But some decays, you don't get the gamma rays, especially for this carbon 14 decay, you don't get a gamma ray. If a gamma ray came out, that would have been very easy for this carbon 14 dating process. But unfortunately, carbon 14, when decays to nitrogen 14, it won't emit a gamma ray because it directly goes to the ground state. So to get a gamma ray, the daughter has to go to a higher level, excited state. Then only when they de-excite, you get a gamma ray, like atoms. When excite electrons, you can get light, infrared and ultraviolet. So always gamma rays comes after alpha and beta decay. Gamma rays won't come just like this, because alpha and beta, gamma ray follows that. So alpha and beta should come before the gamma. So once they go to excited state, then they go down to lower states or the ground states by emitting gamma rays. So this is again same thing. So alpha decay, you have the parent nucleus. If you denote the parent nucleus by X, normally when you want to identify nuclei, you write this A number and Z number. Z number is the number of protons. A number is the number of protons plus number of neutrons. Z number is the number of protons. That is called that gives you the charge of the nucleus. A is called the mass number. Z is called the atomic number. So when alpha decay happens, A number reduces by 4, Z number reduces by 2. So that's why I always tell my students, learning nuclear reactions and radioactivity is very simple, unlike chemical and biological reactions. Here there are very stringent rules. You can't violate them, because whatever happens, Z number has to conserve. Z number has to conserve. Why? Because the charge has to conserve. You can't violate charge. Charge conservation is a global conservation law. Whether it is nuclear physics or particle physics or whatever, charge is conserved. Scientists have never seen any violation of charge. So charge conservation indirectly means Z number conservation. So A number means total number of protons and neutrons. The total number of protons plus neutrons also should conserve. In particle physics, that is called the baryon number. In particle physics, protons and baryons fall into a group called the baryons. Bary means heavy. Bary means heavy. Protons and neutrons are heavier than electrons now. So these are very simple to study because since alpha particle has two protons and two neutrons, its proton number is 2, mass number is 4. Therefore, if the parent mass number is A, it should change to A minus 4. Nothing else. You can't violate this. Z should change to Z minus 2. So A decreases by 4, Z decreases by 2. So these rules you can't change. Unlike in chemistry or biology also, that's why it's difficult. Because you can make different compounds. There are no very strict rules. So this beta decay means this beta minus decay. Beta minus decay means inside the nucleus, a neutron change to a proton. I'll show you later on. So A number does not change. Beta decay means it's basically a change of either neutron to proton or proton to neutron. So when that happens, the mass number does not change. A is unchanged. Z increases by 1. Z increases by 1 means because you emit an electron. So electron has a charge minus 1. So that is called the beta minus. So beta minus inside means a neutron change to a proton. When neutron change to a proton, proton number increases by 1. Gamma decay happens within the same nucleus. Because it goes to the daughter, parent decays to the daughter, it emits a gamma ray. So by emitting a gamma ray, you can't change the nucleus. It simply goes to a low energy. That's all, by emitting gamma ray. So A is unchanged, Z is unchanged. So these are fast and very strict rules. Positron emission is reverse to beta minus emission. A proton change to a neutron. The proton number decreases by 1, neutron number, proton number decreases by 1, neutron number increases by 1. Electron capture again, proton captures the electron. So you lose the charge of 1 and then but you gather electron from the orbit. So therefore again that is A unchanged, Z increases by 1. Z increases by 1 unit. It is actually same mass like the positron emission. I'll show you in the next slide. So these are the, if you want to study the properties of these radiations, gamma rays are uncharged, they are photons. So there is no deflection when you pass these gamma rays in a electric field, positive, negative electric field, gamma rays go through without any deflection, is undeflected. Alpha particles are positively charged, they deflect this way, because since it is positive charge, negative and positive attracts. This beta means beta minus, not beta plus. So beta minus falls or like the positive side. So beta electrons or beta minus deflect this way towards the positive plate. Gamma rays goes through undeflected. Alpha particles deflect the other way. So it's a very simple way of detecting them. If you can detect them because their properties, depending on their properties, gamma rays no deflection because photons, they don't have any charge. Alpha particles are positively charged. Beta particles is beta minus, they are electrons. So this is the same thing that you will have. So you can even use the magnetic field. Even charged particles, when they are moving in a magnetic field also they deflect. But again gamma rays, even though they are moving with the speed, there's no charge. So there's no QVB force. In magnetic field when a charged particle is moving with the velocity and magnetic flux density are perpendicular. They say force is QVB. So if Q is 0, force is 0, alpha particles deflect this way because B is into the page, and electrons or the beta minuses deflect the other way. Alphas are positive, electrons are negative. Now, sometimes we don't know about this. Now, how scientists have found this alpha particle is a helium nucleus? Because you have to find it. No, now we all know alpha particles are helium nuclei. Now, as I told you at the beginning, since they didn't know about these particles, they just washed their hands by naming them alpha, beta, gamma. Still we use those symbols, those alpha, beta, gamma. So this was done by Rutherford to find out the identity of the alpha particle. What is the alpha particle? I mean, you have to know, no, you have to find. Beta particles not difficult because beta particles are the electrons or positrons. So alpha, they didn't know what they were. So he used this decay of radon. Radon emits alpha particles and converts to polonium. Now radon is a gas. Radon is a gas. Most of these naturally occurring radioactive elements, most of them are either semi-solids or solids. But radon is a gas. There's a special school of people sort of studying about the radon, because radon, since radon is a gas, human beings can inhale them very easily. Even radon is there in even building materials, because we get everything from the earth, no, earth crust, even our gas bottles, cooking gas, you have some certain amount of radon. So since it is a gas, we don't know, we can inhale them, we can breathe them. So that those radon gas molecules can get deposited in our lungs. Now, solid radioactive materials we don't eat, no. You have to be a foolish person, no, to eat radioactive materials. But if it is a gas, if it exists in the surroundings, we can't separate, no. We can't say, no, I don't want to breathe radon. So from our nose, the whole air goes in, oxygen as well as other gases. So radon, when radon goes into our lungs, that can cause a lot of damage. So that's why people study about, especially about the radon, because that can cause a health hazard. But this radon decay was actually very useful to study what the alpha particles were, because since radon is a gas, you can get a spectrum. So what Rutherford did was, he in a closed container, he had a radon gas, and he measured the spectral lines. So radon had this this is radon spectral lines. You know, low pressure gases, when you have a high potential difference applied, or called the discharge, it emits spectral lines. And what happened was, actually when you put this radon in a container, he noticed as the time goes on, the intensity of this radon spectral line diminishes. But when you consider when you study the spectral lines, he found the spectral lines uh, which comes from helium. He found the helium spectral lines. So he said, how come? I mean, you put only the radon inside the container. As the time goes on, the radon intensity of the radon line diminishes, or intensity of radon lines decreased, and the intensity of the helium spectrum or intensity of helium lines uh, increased. It developed. So as the time goes on, you lose the radon gas and you make these to helium, because it's a closed chamber. So that's how we found this alpha particles are helium nuclei, because otherwise you can't have any helium inside, no, because nobody has put helium inside the container. It was only radon. But as the time goes on, you see the helium lines are appearing. Helium spectral lines are appearing. And moreover than that, helium intensity of helium lines got brighter and brighter, whereas radon spectral lines got weaker and weaker. And this was also very helpful for Rutherford to do this because luckily the half-life of radon is around 4 days. The half-life was very large. Then to see this effect, you had to wait for a long time. So luckily half-life was 4 days. So after 4 days, the amount of radon goes to half of its initial value. So if since the half-life was very comparatively small, he was able to do this experiment. So this is how he found that helium nuclei, alpha particles are helium nuclei. Because radon, he put the radon inside the chamber, but as the time goes on, radon lines intensity went down, helium intensity or the spectral lines got developed. So from that he found out that alpha particles are really helium nuclei. So this is the same thing actually in this type of examples. Sometimes we give these simple problems to the students. If you start from radon and if it is alpha decay, what is y? It's very simple because you can just do a simple arithmetic. So A has to be 222 minus 4. Z has to be 86 minus 2. So then you look up the periodic table and find out the element. You cannot change this. It's a 100% strict rule. The Z number has to change, A number has to change. So if you lose 4 and 2, the daughter should have A minus 4 and Z minus 2. So that should be polonium. In order to get that, you look up to the periodic table and find out what is the element that corresponds to 84. Is at number 84. So this is this beta minus decay for you to study a little bit more. When a beta minus decay happens, carbon 14 go to nitrogen 14, it emits the electron, and at the same time it emits electron antineutrino. So really speaking, inside what happens is a neutron changes to a proton. This is the simple way to study the beta minus decay. Again, charge has to conserve, no? So neutron has no charge, proton has +1, +1 -1, 0. Neutrinos are neutral. Neutron is neutral. So if you check the charge, charge has to conserve whatever happens. So you have a neutron here, you have proton here. So you have not lost any proton or the neutron. Only thing that has happened, a neutron has changed to a proton, emitting a electron. At the same time, it emits a electron antineutrino. There's a lot of physics inside here. That's why I said beta decay is a three-body process. You share your energy between three people. Alpha decay is a two-body process. Dot and only the alpha particle. So you share your money with only two people. Here you have to share your money with three people. When you share your money with three people, if you lose one person, even if you have two people, if you lose one, you can't conserve. So there's a lot of physics behind this. Even the word neutrino came suggested because when they were studying the beta decay, as I told you, these neutrinos were not detected. So they didn't know about this. So they had big problems when studying beta decay. So because of the non-discovery or not detection of the neutrinos, because they have no charge. So they had a lot of problems with mass energy conservation, linear momentum conservation, and so on and so forth. So there was a scientist called Pauli. Pauli suggested there should be another particle in order to conserve the mass energy, because even at that time some scientists thought in beta decay mass energy is not conserved. Then other scientists said, no, no, don't do that because this mass energy conservation is a, I mean, like our foundation in physics. So don't touch that. So in order to reconcile that, um, Pauli thought that there should be another particle. He didn't know what it was at that time. So even the neutrino word, neutrino means invisible. Actually, it comes from a Greek root. Neutrino means invisible. Later, neutrinos have been detected indirectly. Now, in particle physics, neutrinos also play a very important role in order to comprise or in order to study the what we call the standard model of the universe. So, beta plus decay means inside a proton change to a neutron. Proton change to a neutron, emitting a positron and an electron neutrino. So again, charge is conserved. This so-called the baryon number, the proton and the neutron number is conserved. So this here I have written here. This is called the electron capture. This is if this happens, like in a normal equation. In mathematical equation, you can take one symbol to the other side. When you bring that one symbol, or when you take or bring that one symbol from the other side, it change the sign. So if this is possible, if you want, you can take this positron to this side. When you take the positron to this side, you have to change the sign. Sign means you have to change the antiparticle to the particle, or E plus to the E minus. So that's why I said beta plus decay is similar in a way to electron capture, because at the end of the day you make the same daughter. So you take the positron to this side, it becomes the electron. So in an atom you have ample electrons. Electrons are there in the orbitals. So proton in the nucleus can capture. This won't happen all the time, but there's a probability of capturing someone when they come close. Why not? Electrons are, according to the Rutherford model, electrons move in fixed orbits. But we know that is not true. So electron, we find the probability of finding the electron. So there's a fair chance, or even a small chance, of electron coming closer to the nucleus. When that happens, patas, the proton captures the electron. So that is called electron capture. When that happens, this is same decay. You take this to the left hand side. But here, if you want, you can take this electron to this side. Then the electron becomes positron, but there are no positrons in the atoms. So therefore, this reverse process won't happen here for the similar to beta minus decay. Beta minus decay means neutron change to a proton. So if you take this electron to this side, it becomes the positron, but that don't happen because in atom you don't have positrons. But this can happen because if you take this positron to this side, this change to electron, so proton can capture electron, thereby proton can change to a neutron. So that is called electron capture. So gamma decay, this is a famous Cobol 60. Cobol 60 is widely used in calibration purposes, medical purposes, sterilization purposes, because cobalt is a solid and you can make it by radiation, and cobalt emit very two nice gamma rays. So if you look at the gamma rays, these are the two gamma rays that cobalt 60 emits. So cobalt 60 is a beta minus emission to nickel, but it goes to excited state. If it didn't go to excited states, you don't get these gamma rays. So you have very famous or very prominent two gamma rays, 1.17 MeV and 1.33 MeV. These are the gamma rays people use for even nuclear labs. People use cobalt 60 source for calibrating their detectors, because you have to calibrate the detectors now for energy. Otherwise, you can't measure unknown energy. And this is used in cancer therapy, because you have a very high energetic gamma rays. And the other thing is half-life is not that very small or not very, very large. Otherwise, you have to buy the cobalt 60 every day. And it's a solid, because you never use liquids or gases, because then you can get contaminated if something happens. So these are the gamma rays that comes out from cobalt 60. As I told you, always gamma rays comes after beta or alpha. Right? In order to get a gamma ray, you have to have a transition or emission of alpha or a beta. Then only gamma ray comes. It's a nice, like a ladder thing. Comes to excited state, then only gamma rays are emitted. So that you have to keep that in mind. Sometimes students forget that. They think just nuclei just emit gamma rays, but it comes always after alpha beta emission. This is another picture. So this is the spectrum of a cobalt 60 gamma rays using using the solid state detector. You can see 1.17 or 1173 kilo electron volts. You get a very two nice gamma rays. They are very prominent. And that's why people use this for calibration purposes. Then we come to this different penetration. So alpha particles, you can stop them even if you allow them pass to a paper. Even if you allow them alpha particles to go through your shirt material or a piece of paper, stops. Why? The alpha particles have a plus 2 charge, so it's highly ionizing. So therefore it loses energy. Because to lose energy, you have to interact. No, if there's no interaction, then you don't lose energy. That is true even in human life. When you interact with someone, you lose energy. So alpha particle loses energy even if it goes through a small paper or even a cloth or whatever. Beta particles, they have more penetrating power. They go through paper, but in a metal they get stops. Neutrons, you can it go through this, but you can stop in hydrogenous materials. Water has a lot of protons. So when a neutron collide with a proton, they are even in classical physics, if the masses are compatible, if you have two balls, say with almost the same mass, if one ball is at rest, other one is coming and hitting, the first one stops and the second one ejects. So in order to stop neutrons, people use all hydrogenous materials or paraffin. Even Chadwick used paraffin. Gamma rays penetrate even through concrete, but to stop gamma rays, you should have lead. That's why all these gamma ray facilities, your shielding materials, they use always lead. Lead has a very high Z number. So gamma rays actually loses energy that we don't have time to, because these are photons. Though they interact with matter, there are three things: photoelectric effect, then there's called Compton effect, and then if energy is sufficient, you have a pair production. So alpha particles you can stop inside very easily. So that's why even alpha particle detectors, you should have very thin foils, very thin. Gamma rays doesn't matter; they penetrate. So that's why now sometimes when you have alpha emitter outside, that won't do any much harm into your body, because they stop even on the skin. But if by mistakenly, if you swallow or if you swallow alpha emitting radioactive material inside, that is very dangerous, because then all your organs are exposed to alpha particles. They can ionize the medium, and when you ionize, they can make radicals, and very poisonous things can happen in biological in biology. That is called biological effects of radiation. That is sometimes called the alpha particle or radiation poisoning. Suddenly, if you eat a alpha emitter, that can do a lot of harm into your body. If they are outside, even alpha particle comes, they don't go into your body, they stop in your clothes. But gamma rays can go through the body, they penetrate. Beta particles, they go a little bit further, but they stop because you don't need lead or anything like that to stop beta particles. But for stop neutrons, you need a hydrogenous material. Hydrogenous material means materials with protons, because protons and neutrons, roughly they have the same mass. So when they have the same mass, you can have elastic collision. This neutron comes and loses energy and given to the proton. Even that's how Chadwick discovered neutron. You know, Chadwick didn't discover neutrons directly, indirectly, because uncharged particles, even today, scientists can't detect them directly. To detect them, they have to interact, no? If nothing happens, you can't study a person, no? Even person, people, human beings, he or she has to do something to study. If a person is there, if he does not talk, if he does not smile, then how can you study the person? So if you have a charge particle, then by putting electric field and magnetic field, patas you can measure them because they interact. They do something. They change their path. But neutral particle, they don't change their path. So difficult to detect them. Uh, that's why you detect them indirectly. So this animation, alpha particle stops even in a paper, beta particles in aluminium sheets, gamma rays, to stop them you need lead. You need lead. Now we come to the little bit of mathematics of radioactive decay. So scientists have found if n is the number of nuclei present at time t, the rate of decrease or rate of change of number of nuclei is proportional to the number present. That is obvious, no? If you have more number, you have more comes out. If you have less number, less comes out. So I don't want to go into little bit more because some of you may not understand. But this is where you start. So dn over dt is proportional to n. The number decayed is proportional to number you have. I mean, that is obvious. If you have more money, you can spend more. If you have less money, you can spend less. Right? If you want to spend. Sometimes you don't want to spend. But so the number you spend is proportional to money you have. So dn over dt is proportional to n. But since it is, if you think of only one nucleus, it's a decay, no? So mathematically, decay means you have to put the minus sign. It's not accumulation, it's a decay. So this proportionality you can convert into an equation by putting a constant. dn over dt is minus lambda n. This is the famous equation which governs the radioactivity. Whatever the radioactivity process, whether it's alpha or beta or gamma, this formula holds. Lambda depends on the mode of decay. So lambda is known as the decay constant. Decay constant. This minus sign is there indicating that it is a decrease, not an increase. Now, if you don't put the minus sign here, then dn over dt becomes positive. But radioactive decay is you lose, no, you spend money. When you spend money, you have to put the negative sign. Even in your bank sheet or your ledger, you have to put the negative sign. If you deposit money, it's a plus. If you spend money, it's a negative, no? So therefore, dn over dt is minus lambda n. This minus sign is very important in mathematics. Otherwise, you get a rise. You don't lose and you don't decay, you accumulate. So, so in order to simplify this, so in order to solve this equation, not really simplify, solve this equation, you have to do a little bit of integration because dn, now you take this n to this side, integral of dn is ln n. So if you don't know the mathematics, don't worry about it. But ultimately you get this famous equation, radioactive is called radioactive decay law. N number present at this time is equal to number present at t equals 0 e to the minus lambda t. So radioactive decay follow exponential curve or exponential decay. It's called exponential decay. So it's not linear, it's exponential decay. That means at the beginning it drops faster As the time goes on, the rate of decay goes down, down, down. That is also obvious. No? If you have more money at the beginning, you spend more rate. When you lose money, the rate of spending becomes less and less. So it's exponential decay. And nature has a lot of this exponential behavior. I mean, that's why mathematicians have defined these exponential functions. Now, if you take a cup of tea, say at 80 degrees, and if you keep that cup of tea on in a room, if you measure the temperature with time, you get exponential decay, exponential fall. At the beginning, the temperature drops faster, but when the temperature comes close to the room temperature, the rate of heat loss is less. That is because the rate of heat loss or heat dissipate proportional to the excess temperature. If your temperature in the cup is more than the temperature in the room, the rate of decrease of the temperature is high because your excess temperature is high. But as the temperature comes closer, the rate decreases. That's how nature works. So you have exponential decay. Exponential functions are always, exponential functions. Even if you discharge a capacitor, capacitors also, uh, capacitors discharge the exponential behavior. At the beginning, rate of discharge is very high. As the time goes on, the rate decreases. It's not linear. Uh, it's not linear. So therefore, so this even the charging a capacitor is exponential rise. So exponential functions are very common in nature. Heat flow, even charging, discharging. Even in medicine, you have now, if you have, say, a bacteria, if you give some antibacterial thing, at the beginning, the rate drops faster. As the time goes on, the rate of decrease or the rate of deaths will be less and less. So therefore, radioactivity also follows this exponential behavior. It's not linear. Goes with n equals n naught e to the minus lambda t. Then we defined a term called activity. Activity means the number of decays per unit time. So that is called lambda times n. That means if you have the number of nuclei n, if you multiply that by lambda, then you get the activity. Because activity is the quantity that you measure. Activity is the quantity that you measure. Because number of nuclei you can't measure. You can calculate, but what you measure is what comes out. Isn't it? What comes out. What you measure is how much you spend. Maybe you have a lot of money, but nobody knows. So other people will get to know that you have money because you spend. So therefore, what matters experimentally is the number of decays. So number of decays is actually, if you want, you can dn over dt. So the lambda comes when you differentiate this, e to the minus lambda, e to the minus functions are very easily differentiable. So anyway, activities, n is the number of atoms present at a given time, lambda is the decay probability or decay constant. So therefore, number of decays per unit time is lambda times n. So we have activity equation also same. A is A naught e to the minus lambda t. Where A is the activity now, A naught is the activity at the beginning. Beginning means when the radioactive sample is prepared. That is your time t equals 0 when you make it, or in a sort of say, if you look at the earth when it was formed, you had some radioactive materials on the earth. So A equals A naught e to the minus lambda t. So it also follows activity also drops exponentially. So exponential functions are very sensitive to the exponent e to the minus. So exponential functions means initially the drop is fast, but as the time goes on, the rate of drop becomes less and less and less. Then we define what is called the half-life. Okay, decay constant is also something, but normally we identify a radioactive material from its half-life. Half-life is defined as the time it takes for the activity to fall one half of the initial value. So if you use that same equation, if you put n equals n naught divided by 2, then you get this very famous equation. Half-life is normally denoted by T half. T half is ln2 divided by lambda. Ln2 is 0.6931. So it's a very famous equation, and people even this is very useful in when you do examples. Then 1 over lambda, sometimes known as the mean lifetime. This half-life means time taken for the initial to drop to half. Now, mean life means time it takes. Now, if you use this equation, when when time becomes tau or the mean life, the current value or current activity falls 1 over e times. 1 over e times the initial value. So, sometimes 1 over is about 37%. You know, when you discharge a capacitor also, that is called time constant. Rather than going for half, you can go for 37%. Mostly we work with half values, but even 1 over lambda can be defined as the mean life. The physical meaning of mean life means the time it takes for the initial activity to fall to 1 over e times the original value. So if you put t equals tau, just do that because tau is 1 over lambda, no 1 over lambda, 1 over lambda cancels. A or n equals n naught over e. So these are some of the so units of activity. So SI unit of activity is known as becquerel. Becquerel. Actually, initially the activity was measured by Curie, to honor Curie. Actually, Curie was defined as the number of radioactive decays occurring in 1 gram of pure radium. That was the definition. So if you do this is not a magic number. Actually, if you take 1 gram of pure uranium, you can do this calculation. I am not going to show it. If you know the decay probability, lambda times n, using the Avogadro's number, you can find out how many radium atoms are there in 1 gram. Then if you multiply that by lambda, then you can get this value. So Curie is actually a very big value, Curie. But later on, SI committee decided Becquerel was the person who invented radioactivity. So they thought, therefore, you had to honor Becquerel. Of course, Curie did marvelous job. But therefore, they changed the unit Curie to Becquerel. Becquerel is simply 1 decay per second. There is no reason behind it, just 1 decay per second. To define the Curie, of course, there is a reason. The Curie is defined as number of radioactive decays or activity of 1 gram of pure radium 226. You can calculate that by using mathematics. Then you get this number. So Curie is a very big unit actually. Becquerel is a very small unit, just 1 decay per second. But still in labs and other places, people measure activity in Curies also most of the time because the earlier unit people are very used to. So 1 Curie is 37 gigabecquerels. That's why I say becquerel is a very simple or a very small unit, just 1 decay per second. 1 Curie, if you want to get a 1 Curie, you should have 3.7 times 10 to the power 10 decays per second. That's why I call it 37 gigabecquerels. So this is also the same idea. So this is the illustration of the half-life. If you had 100% Cobol 60, after one half-life, 50% is decayed. Another half-life, another 50%, you have only 25%. Then 12.5, half. It decays to half. So this is the this is the unit conversions, or the 1 Curie is this many number of becquerels. and 1 becquerel is this many number of curies. So you can convert becquerel into curies or curies into becquerel. Whatever it is, that is not a big problem. Becquerel is the SI unit, but still, even in labs, if you go to a nuclear lab or radiation lab, they say in labs, most of the time people use microcuries, not the big activities, because you use that small sources or less active sources to basically do your research and measurements to calibrate your detectors. In radiation facility like sterilization process, gamma rays are very good too for sterilization. Surgical gloves, say cotton swabs. Nowadays, people use them very quite often. No? So you can't heat them. No, you can't heat them because they are all plastic or rubber. So cotton wool is just plastic or wooden, and you have cotton. So you can't use heat to sterilize them. Even when we were small, doctors used glass syringes and metallic needles. When you go and see a doctor, maybe I think young students they don't know about this, but always you will find in a sort of a water container or a water jar these surgical syringes, glass syringes and metallic needles. They use hot water to sterilize, so they put everything in hot water. But because of this, especially the uh, diseases that came into the world, especially AIDS, you can't use the same needle or same syringe for all the people because then you can get contaminated. So nowadays people use plastic things. Once you use, you throw them away. So then there's a problem of sterilization because you can't heat them. So gamma rays are very good for sterilization because gamma rays will kill all the pathogens and bacteria, and there won't be residue. It's different from chemical cleaning because chemicals are not environmental friendly also, and again you can have some residuals after cleaning. But gamma rays, if you have to expose these things to gamma rays, it is very easy to sterilize them. So this is a simple problem. If you have carbon 14 emits beta radiation and start you have 2 grams of carbon. After one half life you have half of it, 3 half life 3 times. So after one half life it reduces to 1 gram and 0.5, 0.25 like that. Then we come to actually this is a nuclear reaction. It's example of nuclear reaction which happens naturally actually, which happens naturally. Now we have lot of nitrogen in our in our outer in the with the in air. You will find you have carbon dioxide and oxygen and nitrogen. So when neutrons bombarded onto nitrogen, normal neutrons are coming from various reactions happen in, sometimes even scientists don't know, they are called cosmic rays. It comes from various reactions happens in outside, not within our atmosphere. But our atmosphere you have nitrogen. So when a neutron is impinged onto nitrogen, it converts to carbon 14 and a proton. So this is example of a nuclear reaction. So this is also very simple compared to chemical and biological reactions. Chemical and biological reactions are very complex. Sometimes you get enormous large proteins and it's very difficult to comprehend. But nuclear reactions are on the other hand are very simple. This is very neutron bombarded onto nitrogen and converting into carbon. So this happens in our atmosphere or every time. This is a natural process. Neutron comes from cosmic rays. There's a lot of nitrogen and convert to carbon 14. So even these nuclear reactions, Z number has to conserve. Very simple. Because here Z number is 7 and 0. Here 6 plus 1. So 6 plus 1 is 7, 7 plus 0 is 7. So you can't make anything else. If there's a missing, if this is missing or fill in the blanks, this has to be a proton. And then a number has to conserve. 14 plus 1 is 15. Again 14 plus 1 is 15. So this is a example of a nuclear reaction. So there are naturally occurring reactions like this, and even scientists use this reaction to make different radioactive materials. That happens nowadays because sometimes you want to make different radioactive isotopes for medical purposes and agricultural purposes and so on. So you can have to initiate a nuclear reactions. Nuclear reactions can be easily initiated using neutrons. Why? There's a reason for that, because neutrons do not have this. Neutrons do not have. We say there's no Coulomb repulsion. What the meaning of that is, neutrons do not have a gross charge. Now it is very difficult to put a proton into a nucleus because nucleus is a positive charge, positively charged. Proton is also positively charged. They repel each other. So you have to push it harder. But neutrons, on the other hand, neutrons do not have a charge. So neutrons can slowly get into a nucleus without any Coulomb repulsion. The nucleus won't say don't come. When if you want to put a proton into the nucleus will don't come. I am positively charged, you are positively charged, I don't want you. But neutrons can slowly get into a nucleus and change the nucleus. So that's why people use neutrons to produce or to initiate or to embark or to make a nuclear reaction happens. That's why all these medical isotopes, people use neutrons, but neutrons are difficult to find. So you should have a research reactor. Research reactor produces neutrons. So when you bombard neutrons onto other nuclei, you can make what you want. That is even you have heard about neutron bombs also. No, nobody has used the neutron bombs. You can release a lot of neutrons into the atmosphere, but neutrons can slowly get into our cells, even plants, because they don't say don't come, because there's no repulsion, there's no repulsive force. So neutron can slowly get into our cells and they can change the nuclei of cells. So therefore neutrons, working with neutrons are very dangerous. Yeah, people have to be very careful because there is no charge, gross charge. They can slowly get into the nuclei of cells. And this also has other important application. This is called carbon-14 dating, because um, in the Earth atmosphere we have carbon-14 also. Carbon-12 is the stable isotope. So all plants absorb carbon dioxide. So normal carbon dioxide, you have carbon-12, but there's a small percentage of carbon dioxide with carbon-14. Because these chemical and biological reactions, actually they don't identify radioactive nuclei. That is also a good thing and bad thing. Now when there is a radioactive substance coming into our body does not know. Body does not react. Now when a bacteria or something comes, the body has a defense mechanism. But when a radioactive element comes or nuclei come, actually biology and chemistry do not know about nuclei in a way. They know only about the electrons in the atom. So our body does not distinguish whether it's a radioactive element or not. It goes through the normal processes that the nature has given us. So in a way, it's a positive sign is you can use them to cure things. The bad side is if you have radioactive material and if you without your inevitably or without your knowledge, if you swallow it or something happens inside the body, there's no defense mechanism to work against the radioactive nuclei, because it's a nuclear thing. Chemical and biological reactions work with only the electrons. So radioactive element carbon 14, some percentage is there in our normal carbon dioxide as well. Actually, it's isotope. No, now you know if you take isotopes, there are isotopes. Now, hydrogen has hydrogen, deuterium, tritium. It's like isotopes are like brothers and sisters in the same family. You want to replicate them. So any element has its own brothers and sisters. Your Z number is same, but you can have isotopes. So carbon dioxide, you have instead of normal carbon, you have carbon 14. So therefore, in our body, when we are living, we have a certain amount of carbon 14. You can't avoid it. So when you are living, you eat, you go to the toilets, and so your carbon 14 percentage is roughly a constant unless something happens in the atmosphere, even some supernova explosion or something, suddenly carbon 14 percentage can go up. Other than that, normally the carbon 14 percentage is balanced because you eat, you go to, you excrete your things, and again you eat. But once you die, you don't eat, no. Once you die, you don't eat. All your metabolic things finishes. Then the carbon 14 in you, it decays only. There's no replenishment. There's no accumulation. When you are living, you excrete but you eat. So therefore it's balanced. But once you die, it only decays. So using that decay, scientists have used that decay to find out age of this archaeological sample. Because in everything we have carbon, no, we are carbon based animals, no. We have carbon. We human beings have carbon. Trees have carbon. That's why you have organic chemistry, not different chemistry. So we are made out of basically hydrocarbons. So once you die, you don't eat, then your carbon 14 decays only. So this is the decay of a carbon 14 nucleus. As I told you earlier, the carbon 14 unfortunately won't emit a gamma ray. It emits only an electron. That is the difficulty of detecting this. That's why you have to have special labs to to have this carbon 14 dating. Or if you had gamma rays, then of course it would have been easy to anyone to do this. But it won't emit a gamma ray. So this is the same thing. Neutrons in cosmic rays collide with nitrogen, formation of carbon 14 combines with everything because basically we eat what is produced in trees now. Even animals, even if you eat flesh, they also eat plants or subsidiaries of plants. So we all have the same carbon 14 percentage. But once you die, uh, then your carbon 14 intake stops. Then it decays only. So this is a animation. You know how many carbon 14 atoms present. It's a small number. Now this yellow dot resembles 1 trillion carbon 12 atoms. Not only one carbon atom, 1 trillion carbon 12 atoms. The orange one represents 1 carbon 14 atom. So you can understand the composition. The percentage wise, this is very, very, very small. Out of this 1 trillion carbon 12 atoms, how many carbon 12, 14, 1, 2, 3, 4, 5, 6, 7, 8, like that. Because this yellow dot does not represent 1 carbon 12 atoms, is 1 trillion. Out of 1 trillion carbon atoms, carbon 12 atoms, you have only very few carbon 14 atoms. So now if you want to date back this carbon 14, because carbon 14 can be used to date back the archaeological samples, but they have to do a special procedure for this because it won't emit gamma rays. So you take the archaeological sample, then you burn it, and then you convert into the gas. Now, in a gas, you can measure this beta minuses. That's the difference. If you have a solid material, these emitted electrons, how can you measure? because these emitted electrons in the decay of carbon 14, they stops inside the sample. They won't come out. So you can't get the exact number of counts. So you can't because you can't date it back because some electrons, in fact, very few electrons might come. They will get stopped inside the sample. But when you burn that small piece of sample and convert into a gas, then you know gas is you can have a low pressure. You can increase the volume and make it low pressure. When you have low pressure gas, even when there are beta minuses, you can detect them. You can detect them because it's not a solid. In solid, the beta minuses stops. In gas, if you have a dilute, low pressure gas, you can detect the beta minuses with high accuracy. That's why this process has to be there. Just by uh, measuring beta minuses given now from a sample, you can't date back because you lose lot of electrons. You can't detect them. You can't detect everything. Only very maybe one or two you can detect. All the others get stopped inside. But low pressure gases you can easily detect the beta minuses because they will come out from the low pressure gases. So therefore you can detect them using a beta or electron detector. Now in nature there is something called this naturally occurring radioactive series. To start with uranium, it emits alpha particles, beta and decay like steps, and stops at lead. They decay, there's a chain of decays. This happens every day, every time. This decay happens in that is called naturally occurring radioactive series. Even if you at the beginning of the earth, if you had only uranium, now it has decayed, and we have all the other elements as well. So sometimes students ask me why stops at lead. There's a lot of physics there because lead is a closed. In gases you have something called closed shell atoms, and closed shell atoms are very neutral, like argon, krypton. So lead also similarly in a nucleus. Also there are shell closures. Now helium atom and helium nucleus are very stable both. Why? Because helium atom, it has only two electrons. Two electrons means the first shell is fully occupied. There are no vacancies. If the third electron comes, it has to go to the next level, next story. Your rooms are closed. You can't, there are no vacancies. So therefore, that's why we say helium gas is very inert because the shell is closed, there are no vacancies. Sodium, on the other hand, that one electron is there, he is always willing to get joined to someone else. So it's active. So similarly, helium nucleus also you have two protons and two neutrons. So thereby even helium nucleus is also very stable because even nuclear shells are closed. That's why helium is neutral or very inactive in nuclear sense as well as atomic sense. That's why even some heavy nuclei emit. Sometimes students have this question, why they emit alpha particles? Why not something else? Because alpha particles are very stable. So nature always does things to get stability, to achieve stability, releases energy to achieve stability. So it does not want to emit something which is unstable because then you create more instability. Heavy nuclei emit things because to get stability, no. Otherwise there is no end to this periodic table, no. Otherwise chemistry will be very difficult, no. If you have about 1,000, 5,000 elements, but nature has controlled that. If you go to heavy elements, if you put more protons inside the nucleus, they become unstable because the protons have tremendous Coulomb repulsion. So when they are unstable, they emit things. As I told, like human beings. When you are unstable, you blackguard others. You try to hit the others or you do something else to lose your energy. So lead is something, a nucleus similar to helium is a closed shell. So lead is very stable. So that's why there's now after decaying from uranium, thorium, all these things end up at lead. That's why it end up at lead. Because once you find stable thing, nature stops. Nature does everything to achieve stability. Even cyclones and other things, nature, if you put more heat to the surroundings, and there is a way of dissipating this. So that's how nature works. It tries to have a stable system or stable status rather than unstable status. Even in our life, we also like to be stable, no? That's why you learn. That's why you learn. That why you learn, because you like the subject, or you want to get a good job and become stable. To have a to get a good job and then have a family and then live happily. So even human beings like stability, no? We don't want anything, even our life, to be unstable. We do everything to achieve stability. So nature is also like that. So here also something very important. If you plot the neutron number and the proton number of existing nuclei in the or atoms in the world or in the universe, this is called the line of stability. So at the beginning, all stable nuclei, they have neutron and proton number same. Carbon, oxygen, if you take carbon 6,6, oxygen 8,8. So their neutron and proton numbers are same. But as you go to heavy nuclei, you need more neutrons than protons to achieve stability. Because by putting lot of protons, you increase the Coulomb repulsion. So therefore, the line of stability curve deviates. So initially it's a straight line with 45 degrees. Because low mass nuclei, you have same number of neutrons and same number of protons. There's no majority minority difference. We have same number of protons, same number of. But unfortunately, nature can't achieve that when you go to heavy nuclei. Because you need more neutrons than protons to counterbalance the Coulomb repulsion. But even there you have a limit. So when you go to heavy nuclei, everything in this in the world decays happen because they want to come to this stability line. That's the reason. This is called line of stability, or like a heaven. This is line of stability. So heavy nuclei, they emit alpha particles and comes to this stability line. So they have to emit a chunk. The nuclei line below this stability line, they emit beta minuses, because by emitting beta minuses, neutron change to a proton. So if you are here, how can you come to this place? If you are down here, it's like a mountain or slope. If you want to come here, you have to go this way now. So if you want to go this way, you have to lose the neutrons and increase the number of protons. That's why the unstable nuclei below the stability line tends to beta minus decay. You understand the reason? Because these guys, they like to come to this stability line. That is their final ambition. So in order to do that, they have to reduce the neutron number and increase the proton number. That is a beta minus decay. If you are sitting above the stability line, then how can you come to this line? By coming this way diagonally. Then it should lose us protons and increase the number of neutrons. That is beta plus or electron capture. Now I think you understand why nature has all these processes. These guys, these guys can't go this way and that way, because they are at the far end. When they are at the far end, they have to emit a big chunk, that is alpha particles, and then come to the stability line. If you are somewhere here, you have to jump to this place, no? But if you are somewhere here, you have to jump this way. If you are here, you have to jump this way. So if you want to come to this line, you have to have beta minus, because beta minus means your neutron change to a proton. Beta plus means a proton change to a neutron. So unstable nuclei lying above the stability line tend to have a beta plus or electron capture. Unstable nuclei lying below the stability line tends to emit a beta minus. So now you understand why this alpha beta and beta minus and beta plus happens. Of course, gamma decay happens. I have already explained earlier. Okay, so this is actually a very famous initiation. You know, this was done by Irene, daughter of Marie Curie, Irene Curie and Frederick, her husband. They also did a lot of experiments on radiation. So they allow alpha particles to incident on aluminium, and suddenly aluminium became phosphorus. So this is the world first artificially produced radioactive element. This is artificially produced by this is a nuclear reaction in a way. This is a nuclear reaction. Of course, they had alpha particles. No, maybe just for fun, I don't know. Just for fun, they uh, shot alpha particles onto aluminium. Then they found aluminium changed to phosphorus. This phosphorus was radioactive, and you get other. So this is the world's first artificially produced radioactive element. So these alpha particles onto aluminium, phosphorus. Phosphorus is radioactive. It emits beta plus emission. And this experiment was not only the first to confirm the existence of positrons, but also neutrons, because this is also one way of getting a neutron, which had been proposed 2 years earlier by Chadwick. You know, neutron scientists knew there is some other particle inside the nucleus. They knew about it because they knew proton alone uh, could give you the stability of the nucleus, because proton they are positively charged. Of course you need the positive charge because you have electrons in the atom. So to have otherwise there's no Coulomb attraction, there's no binding force. So proton should be positive, but you can't put lot of protons inside the nucleus because they repel. So to counterbalance or dilute the Coulomb repulsion, scientists knew they had to have some other particle, but they didn't know what it was. But of course, they knew it has to be neutral because you don't want any other charge inside the nucleus. Already there's positive charge. So neutron means like neutral, no? Positive. Proton means like proton, positive. Electron means it carries the electricity. So electricity was discovered much earlier than the electron discovery. Scientists knew electricity. So electricity is produced basically in a conductor by the flow of electrons. So this was one of the first nuclear experiment, or sorry, nuclear reaction that scientists have made. Of course, the earlier carbon-14 production that happened naturally anyway, but this is the first man-made nuclear reaction, I would say, and first man-made artificially radioactive element. Okay, so thank you very much for listening to this lecture. If you have any questions, now it is the time to ask. Okay, thanks and goodbye.